Who are we missing? We're missing Ryan, Chris, and who else? Somebody else. Brian. Brian will probably be here. Okay. So take a look at your opportunities. Okay. All right. Are there any questions on? We can go through these. First one, number one A. One of the ways to several ways to fix it. One of them is one way to fix it is just call the probability of A union B equal to the probability of B, because the probability of A is 0. You could also just simply change the union to the intersect, right? That would also work. Any questions on 1A? Number 1B. A lot of you changed it. Just say that they're not the same. Well, at first, I'm like, that's kind of a weaselly way to answer the question because the question is false or the statement is false. So just changing it to a are not. Well, but that's still not correct, right? What if you rolled a die, a fair six-sided? We already know that the mean value, the average value, is 3.5, right? We've done that a couple different ways. It's 3.5, right? On the average, you're going to roll a 3.5. So what's the median value? Well, n is even, right? N is not odd. N is 6, so it's even. So what you do is you take the average of the two middle values. Okay, so if n is 6, you take the average of the third and fourth values when they're put in ascending order. Well, the median value is the average of 3 and 4, and that's still 3.5. So they could be the same. So if you said they're not the same, I took a point off. Okay. The most correct way of fixing the statement would be something like could be the same, or something like that. You could say that outliers affect the mean, which actually goes into number 1D as well. Okay, but there's several ways to fix it. But to say that they're not the same is not entirely correct. Does that make sense, guys? Yep. Yep. If the data set contains outliers, more than likely they're not the same. If it doesn't contain outliers, then I hope it's obvious to you that they would be much closer together, if not the same. So, okay, number 1C, two independent events, A and B, are mutually exclusive. Well, that's a false statement. Generally, they are not mutually exclusive. In fact, I can't think of any case where they would be. If they're independent, there's several ways to fix it. You could change the word independent to disjoint, right? That would fix it. You could change it instead of are mutually exclusive. You could say have an intersection whose probability is the product of the individual, whatever. There's several ways to fix it. Number D, outliers affect the median value. The easiest way to fix that one is change median to mean, right? That's the easiest way to fix that. And number 1E, if two events are independent, probability of their intersection is sum of the individual probabilities. That's not the probability of the intersection. The probability is of the union, right? Because they're mutually exclusive. You just add the individual probabilities. So that's the easiest way to fix that. Okay. Any questions on number 1? Number 2. This is the question where Brandon is trying to eliminate everyone in the local vicinity. Is that true, Brandon? You have habanero flavored buns. Who gets those?
I think it might be interesting, I guess.
I like habanero.
Oh, man. I suppose they could be interesting, but if you're expecting so would a habanero flavored bun, would it be like white bread or wheat or rye or, would it be the consistency of just a white bread kind of bun? I don't know. Is a habanero pepper, is that the yellow one? Or is it green?
I think
Or red?
habaneros are like orangish.
Orangish?
They're like tiny, like shriveled orange pepper things.
Wow. Now they're hotter than a jalapeno, right?
Yeah, I think they're the hottest naturally occurring pepper in the world.
As opposed to what's hotter?
Like Carolina Reapers and the ghost peppers and stuff. Those are made by humans through they weren't naturally occurring. They were made by geneticists and stuff.
To what? Punish people?
Yes, to specifically try and make the hottest peppers in the world.
To punish people.
Yeah, they get contracted by like hot sauce makers and wing companies and stuff to make hotter and hotter peppers. I think there's somebody who's like super famous for making them. He's like the one who has made like the Carolina Reaper and the ghost pepper, and he's got like some unnamed ones currently that he hasn't released yet that are even hotter.
So what's his last name? Satan?
I don't know. Wouldn't be surprised.
That just sounds like oh man. That just sounds like maybe, I don't know. I mean, yeah. Inflicting as much pain and misery on people that are eating food, right? And they volunteer.
Must love doing it.
You must. I don't know, man. Wow. Yeah, I didn't know the ghost pepper was genetically altered. I thought that was a naturally occurring one that
I didn't know either until like about a year ago. I found out that like somewhere like the habanero is supposedly the hottest naturally occurring pepper, and all the other ones have been made by people.
People that have something wrong with them. But anyway. Okay, so Chris isn't online yet. Oh, Chris, you are online.
Hey,
I sent your graded opportunity via email. So
okay, thanks.
if you check your email, you'll see it. So Chris goes to Brandon. Brandon or Chris, is your stomach like bulletproof?
You would think so.
I guess. I don't know. So anyway, guys, this is just like the number of sandwiches that are available at Subway. Okay. So you got one of two kinds of bread you could have, or buns, I guess. And then I changed the numbers in the various versions. The answer is either 120 or 84, depending upon the version that you had. Okay? At least one of you figured that you could have any number of the toppings. So you did a 7 factorial, which would make sense in that case. And I graded it correct because the question really didn't say. Any questions on number 2? Number 3. This is just like the one that we did. Was it last week? I think. The answer is either 2/3 or 3/4, depending on the version that you have. Does that make sense? We did. I was careful in choosing the numbers that I gave you. I wanted you to be able to do it. You could easily do this one without a calculator. So anyway, any questions on the first page, guys? Okay, going to the next page. Brian has a significant other who I have met. Brian's not online. I wish he was. Okay. This is similar to the homework question where the family's going on a road trip, right? And they could have problems along the way, and you had to figure out some probabilities, or at least define the. You had to define some of the areas. So the Venn diagram looked like your classic Venn diagram. There is space outside of the events: flat tire, cracked windshield, and overheating. In other words, there is a non-zero probability that Kirsten could have none of these problems. Since they're independent, you find the intersections by multiplying the individual probabilities, right? So the probability that she has a flat tire or overheating, that's just the probability of a flat tire plus the probability of her overheating minus the intersection of the two, which would be the product of the two. Okay? Does that make sense? And any questions on the Venn diagram or number B? Okay, number C, only a cracked windshield. There's a couple different ways to do this. The way I did it was I took, probability of a cracked windshield. Okay, so that's a certain value. I don't remember what it was. The one I'm looking at has a probability of 0.15 for it. The other version had what? I don't remember what that probability was. Huh. Who had the other version? What was the probability of a correct windshield if it wasn't 0.15? Or was it 0.15 for everyone? I don't remember. I think it's 0.15 for everyone. Okay. So 0.15 minus the intersection of flat tire and windshield, right? So you got to multiply those two products. You got to find the product of those two probabilities, subtract it off. minus the probability of a cracked windshield and a flat tire. So you got to multiply those two probabilities. Okay. And when you do that, you have to subtract. No, that's right. Oh no, you have to add the probability of all three, right? Is that how I did that one? Yeah, you have to add the probability of all three events. Do you see why, guys? Do you want me to do it on the board? Number 1C. How to find the probability of only a cracked windshield. Do you want to do it on the board real quick? Because there was a lot of answers that were all over the place for D and C on number 4. Okay. Esteban, I think you got that right, but sounds like you were a bit Okay. So here's your sample space, guys. Right? So Kirsten could have a cracked windshield. Yes, no? You buy that?
Mm-hmm.
She could also have a flat tire. Can you see the green? Does it show up in the camera?
Or I can make it out.
All right. Well, I'm not getting a warm fuzzy from you, so I will use this color. This is a little better, is it not? Yes, no?
Mm-hmm.
And then she could also have an overheated engine, in which case, if I were her, I would just cut the trip short and go home. Anyway. So, guys, what's the probability that she ends up in here? Well, we have the probability of a cracked windshield, right?
Yeah.
So that's a good starting point. Okay. Then we subtract this area out because it's the intersection. Do you buy that? We subtract this football region out. Does everyone understand that and understand why? You guys are not giving me a warm fuzzy.
Yeah, it's kind of hurt
for me.
Yeah, it froze for me too.
Yeah, it must be on my side. Sorry, guys. Is it back up and running? And okay, I don't know what happened. So, do you see that we're going to take this football region out, right? Do you see that? Because it doesn't fit only W. We also have to take this football shaped region out, right? The intersection of W and F. Do you see that, guys? So and do you see that when we have the probability of W, which includes the whole bubble, right? Then we subtract this football region out, and we subtract this football region out. Do you see the problem? We subtracted the intersection of all three out one too many times. So we have to add the probability of all three. This is the expression for finding only W. Okay. So, do you understand how to get number C if you didn't get it originally, or even if you did, but you were a bit unclear? Do you see how it's done? Yes, no? Talk to me, guys. Now, the probability of only one of the events, a couple ways to, well, there's really only one way to do it, but you can either, one way to do it is to find the probability of only W. Well, you had to do that to answer number C, okay? And add to it the probability of only H, and add to that the probability of only F, right? Do you see that? Yes, everybody? We good?
Yeah.
Okay. Now, if we do that, and add everything up, what you're going to end up as an expression is this: probability of a cracked windshield plus the probability of a flat tire plus the probability of her engine overheating, right? This marker has about had it. Then, and here's the tricky part. We have to subtract out the intersection. We already know that, right? Because the intersection means she has more than one thing happening to her car. So, but you have to subtract out 2 times each intersection. You subtract it out once for only W. Well, you're going to subtract this out again for only H. Do you see that? So you got to subtract out the intersections twice. 2 times the probability of H and a flat tire minus 2 times the probability of a flat tire and windshield. Now, do you see? We got to do one more thing. Anyone see it? Think about the intersection of all three. We added that intersection in 3 times, did we not? Up here. This area here got added 3 times. Well, it gets subtracted twice here, doesn't it? And it gets subtracted 2 more times here, and it gets subtracted 2 more times here. So we're adding it 3 times, we're subtracting it 6. So what do we do with it to make everything work? I get 3. We don't want to include it, right? We don't want to include it, so we add it 3 times, subtracted out 6. If we add only it 3 more times, then the net result is we are omitting it, right? So if you do the math to solve that, you get the final answer, and I don't remember what it is. What is that answer? I don't remember. Yeah. Yeah, And that's what we want, because we only want the probability of one event. So we definitely want to exclude the probability of all three, just like we want to exclude the probabilities of any pair of events. Just the middle. Okay? Yeah, which is what when we found the union, we had to add it back in once, I think. When we found the union of H, W, and F. Remember that? We started with this, and then we subtracted each intersection out once. And then we added the intersection of all three once. Because we added it 3 times, we subtracted it 3 times. So, but this is different because it's the probability of one and only one event. All right? If you do the math, you'll see that when you find the probability of only W and add to it the probability of only H and add to it the probability of only F, when you do that, the expression reduces to this. I'm looking for the. So anyway, that's the way I did number 4. I don't remember what the answer is. Let us see. Let's go on to number 5. The tree diagram turned out to be a nightmare. Sorry, guys. I'm really sorry about that. I should have had, and actually I thought I had, but I screwed up clearly. That you rolled the die once, and you flipped it twice if it was, or something like that. If you only roll the die once and flip it twice, the tree diagram is a lot better, right? Anyway. So the answer to number B is 1/12. The answer to C is 1/4, because there's 3 different ways to get tails in an even number. There's 3 different ways, so it's 3 times 1/12, which is 1/4. And the probability of number D was 1. I think did I change that? 1/72nd, right? 1/72. Did everybody get that for number 5? D. 1/72, right? Yeah, I think that's true of both versions. Okay. How many ways can we scramble the letters in hot and spicy? Number A is nothing more than 9 factorial, right? Because there's 9 letters. So it's 9 factorial. There's 9 choices for the first, 8 for the second, so on, right? Number 6B. A lot of you found the permutation of 6 letters, but it says combination, so you have to treat it as a combination. So if you found the permutation, you need to divide by 6 factorial. Okay. Some versions, I think I had to find, I had to use 5 letters, didn't I? Is that true of some of you? Order does not matter in a combination. Yes. Yes. So you got to divide by however many letters you're supposed to find. I think I had you find either 5 or 6 letters, right? In number B, 6B. Yeah, some of you had 6, some of you had 5. So the answers are different. Then you have the word adissimilar, which I have no idea if that's really a word. It probably is not. Anyway, and this is about as close to a curveball question as you'll ever see me give, at least on purpose. If, the way to handle the repeated letters is there's 11 total letters that you're given, but there's a pair of S's, there's a pair of A's, and there are 3 I's, are there not? So you have to take 11 factorial, because if everything was unique, that's the number of permutations you'd have, would be 11 factorial. But since there are 2 S's, you divide by 2 factorial, because there are 2 factorial ways to arrange the 2 identical S's, right? So you divide by 2 factorial for the S's, you divide by 2 factorial for the A's, and you divide by 3 factorial because there are 3 lowercase i's. And you end up with, what do you end up with? I don't have the answer in front of me. So 11 factorial divided by 20, 24, whatever that is. Whatever you get when you do that math. And there's actually a couple examples in the book on how to work something like this out. I believe it's 1,663,200 ways ways to arrange the letters. So 1.6, 1.7 million and change. Okay. Yeah. Yeah. It's in your. There's some examples in your book in chapter 2. Number D, I actually did you a favor. This time the 2 S's are different. One's upper, one's lower. And the 2 A's are different. One's upper, one's lower. And you only have 2 of the same letter I. So it's 11 factorial over 2. And that's 19 million and change, almost 20 million. Okay? Any questions on that? That was number 6. Number 7. Are we good? Okay. Number 7. I can't read. Okay. Oh, the temperatures. Okay, that's right. So the mean value, depending on the flavor of the opportunity that you have, the mean value is, that's not it. 5.5 Is it 5.5 regardless of the flavor that you had? Oh, I'm sorry. It's either 4.7 or 5.5, depending on the version you have. The median is either 3 or 3.5. I shouldn't have had 2 3s in there, and I'm kicking myself for I should have made one of the 3s a 2 or something like that. So you'd have to do some averaging anyway. I mean, it's still a valid question. So that's number 7B. Number 7C. Guys, what I was looking there for was there's outliers in the original data set. You have, I got it. I have to find a different version. Go, Esteban. The average of the two. Yeah. Yep. Yep. What'd you have? They should be. Hang on, I can look at yours. Yeah, they're okay. Let me take a look at yours. -10, 7, 12. Okay. You had 5.5. If you arrange them in order, you have the average is 4 and 3. The two middle values are 4 and 3. Yeah. Yeah. They are not in order. You're correct. Yes. No, they are not in order. You have to put them in order. Yeah, there are 2 outliers in both versions of the opportunity. Those 2 outliers are 21 and 28. Okay. They heavily skew the mean value high. Do you see that? I mean, if you omitted those 2 values, what would your range be? -10 to 12, yes, no? If you omitted those 2. So 21 is certainly quite a bit away from the bulk of the data. 28 is even further away. So they heavily influence the mean. Okay, so I was looking for outliers basically that for number C. The outliers skew the mean in the positive direction. Okay. Variance, you simply take the deviations, square them, divide by 10. I'm sorry, 9, 10 minus 1. And then you take the square root for the standard deviation. Okay. Any questions on number 7? Number 8. Depending on the version that you had, the Venn diagram and the tree diagram. Hopefully, you understand what's going on with those. Okay. You, regardless of the version you had, to answer number C, the given condition is that a student passed, right? So for number 8C, you're finding the probability that they didn't study given that they passed. Okay. So you have to find the probability that they pass, which is the probability of passing and studying, plus the probability of passing and not studying. Okay. So the denominator for part C is grossly based upon the probability of passing and not studying is pretty small. The thing is 1 out of 80, is it not? Yeah, that's right. It's 1 out of 80, 1 over 80, or 0.0125. So that's the probability of passing and not studying. Probability of passing and studying depends on the flavor that you had, but it's pretty high. So you add those two and you get the denominator. Let me see if I can find it. In one version, it was 31 out of 60 downstairs. In the other version, it was, I think it was 49 out of 80 downstairs, I think. So then it's upstairs. It's just the intersection of passing but not studying, which is 1 out of 60 or 1 out of 80. So it's a pretty low probability, and no matter which version you had, it's a really low probability. It's like definitely less than 10%. It's either 0.02 or point. Oh man, I just had it. 0.02 or just 0. It's either 0.02 or 0.032 and change. Okay. I didn't mean for D to pull. Number D is just 1 out of 20 or 0.05, which is the last sentence in the question. And number E, are they independent or dependent? They're dependent. If you look at the conditional probabilities, they are different than the individual probabilities. Okay, so that's what's going on there. Are there any questions? I was pretty happy, guys. I was pretty happy overall. Grades weren't that bad for the most part. So you guys did good. Last chance to ask questions about the opportunity, guys. Last chance. Talk to me. Okay, Chris, you okay?
Yeah.
You don't sound okay.
So on 8C, it's like if a student passed, what's the probability they didn't study? Wouldn't that be the union of didn't study and passed divided by the total amount that passed?
It's the intersection of didn't study and passed.
Right, the intersection of didn't study and passed.
Yeah, the intersection. Yeah, not the union. Did I answer your question?
Ah, crap. That's where I screwed. Okay, I see where I did.
I think the light bulb turned on.
Yeah, I got it.
Kenny, you direct message me. I will take a look at that. Okay.
Yeah, thank you.
Yep. Okay. Can we put opportunity 0 to bed? Again, guy, I was really, really happy with overall scores. I was. That means you guys are doing your job and I'm doing mine. So Good. Ready to talk random variables again, guys? Talk to me, guys. Come on. I know it's Tuesday. I don't remember where we left off. You're going to have to help me. Did we finish whatever example we were doing? Okay, are you ready to do a continuous random variable kind of situation? Or, okay, this one was an easy one, I think. It was an easy discrete, right? Just as an example.
Ready to move on?
So we can do one of two things. We can either we can take a look at another discrete example, or we can go to a continuous example. Your call. Talk to me. We did. Yep.
Did we ever finish part D of our last example?
What was part D? I don't know what it was. So you're gonna have to help me.
It was find cumulative distribution function f of x.
Oh, we did not. Okay. Thank you. Thank you, Brandon. What was lowercase f of x? Didn't we find the distribution function? Yes, no? Didn't we have x and what f of x was? For 0, 1, 2, 3, and so on. I don't even remember what x is, guys. That's how bad my memory is. Were we rolling a die or flipping a coin or something?
I think we were flipping a coin because x was 0, 1, 2, and 3.
Well, it was probably an unfair coin, wasn't it? It's right, 2/3 and 1/3, right? Probability of a heads.
Yeah, probably ahead was 2/3.
And what was x? The number of heads or the number of tails? And was it 3 tosses?
I believe it was the number of heads in 3 flips.
Okay. Didn't we fill out this table?
Yeah.
Because if x equals 0, that means we flipped it tails 3 times, right? Didn't we get 1 out of 27 for that? Because it's 1/3 cubed.
Yep.
And if we flip it 3 times, we can also get 3 heads, right? And that would be 8 out of 27 because we would flip it 3 times. So 2/3 times 2/3 times 2/3 is that value right there. Yes, no? Right? What's the probability of 1 head? Well, there's 3 outcomes, right? We did this on Thursday last week, didn't we?
Yeah.
Yeah, I remember doing this. So all of these are equally probable, right? Probability of any one of these three is the same because the coin tosses are independent of one another. So it's really 3 times any one of these numbers because they're all the same. Probability of flipping a heads once is 2/3. And probability of flipping tails on the other two tosses is 1/3 each. So it's 3 times 2 out of 27, which is 6 out of 27. Is that ringing any bells, guys? Talk to me.
Yep. That seems familiar.
You should have it written in your notes. What's this value here? Probability x equal 2.
For that, we had 12 over 27.
Okay, that's what I thought we would have, and I don't remember doing it at all. Thursday was a long time ago. So how did I know it was 12 out of 27? Other than it's 3 times 2/3 times 2/3 times 1/3, right? There are 3 ways to do it, right? You do this math, you get 12 out of 27, but we really don't need to, do we? If we do 1 minus that, minus that, minus that, we darn well better get this value, shouldn't we? Talk to me, guys.
Yeah.
All 4 of these values should add up to 1. That's the one thing that is unchanging in statistics. Okay? X can only equal one of these 4 values. So if we add up these 4 probabilities, they all add up to 1. They have to. Okay, guys? Does that make sense? Talk to me. We good?
Yep.
Yeah.
Okay. Can I get rid of our work here? I'm going to leave our table and that up there, the introduction. But can I get rid of these 2 statements?
Mm-hmm.
Going once, twice. Okay, now, cumulative density function, CDF. Or for discrete, we might call it the distribution function. Okay, we call this the CDF. What is the name? Take a guess. What do you think it means? What does the word cumulative remind you of?
Total.
Total? Okay, is it since time began to when time ends?
Yeah. Or since time began until right now.
There you go. So, like, if you have a cumulative GPA, right? That's from when you entered college up to the current time. Yes, no?
Yeah.
Right?
Yep.
So, this is a function that gives us the amount of probability mass. And with discrete, we don't think of probability mass, but it really is, okay? That has accumulated up to the value lowercase f, because it's PDF, f of x equals x. This is not I didn't screw up. This is a valid notation, and I'm going to explain it now, okay? The term f of x equals lowercase x. Again, not a typo. This is the value of f of x at a specific value lowercase x. Capital X is a random variable. It takes on any of these values, okay? So if we say f of x equals lowercase x, this is the general form of f of lowercase x, okay? So, does everybody understand this? We're going to do some examples, and it's going to be pretty obvious. Can I get rid of our definition? Does anybody want to take a picture and throw it in the chat? Because I need to get rid of this so we can calculate our CDF. Going once.
I think I got a picture of it.
I see something in the chat. I'm going to get rid of this, okay, guys? Going once, twice. Okay, so you know what the CDF is, what the definition is. Now let's actually use it so you have a better understanding. Okay, here we go. And it's denoted capital F of X. Okay? If you see capital letter, guys, we could have capital G of X. We could have anything. If it's capital, it's CDF. Lowercase, it's PDF. Not to be confused with a file format supported by Adobe, right? Anyway. So, I should have written this lower. Can I erase this? Do you guys see it now? I mean, there's nothing earth-shattering here, right? I need to add another row to the table for a CDF. Okay. So again, the cumulative density function is a function of probability mass that is accumulated up to now, up to a certain value. So this right here is capital F of 0. How much probability mass has accumulated thus far from negative infinity all the way up to 0? Isn't it 1 out of 27?
Yeah.
The cumulative of 1, what do I put here, guys?
Seven out of 27.
Guys, it's not rocket science here, right? Yes, no? What's here?
19 out of 27.
And then if we hit 3,
27 out of 27.
1.
which Kenny says is 1, and he is 100%. Okay? So, let me silence my ringer. I apologize, guys. Okay. So, do you see that f of x equals 0 for x, for values of x that are below the minimum value, right? Before you've accumulated any probability masks? Do you see that, guys? So, like, we start accumulating probability mass at x equals 0. So, for any negative values of x, the cumulative is 0, right? We haven't accumulated any mass yet. What's f of x for values that are greater than or equal to the maximum value of x? Goes to 1, doesn't it? Right? Greater than or equal to the range. So, guys, we can plot this, okay? You want to plot this? We can plot the PDF of x versus x. We can also plot the cumulative of x versus x, okay? So that's what I want to do next. You ready to roll?
Mm-hmm.
Yes, no? I'm going to erase this f of x stuff, okay? So we can put the graph right here. So, if we're going to do a chart, I'm going to omit negative x, or I'm sorry, negative values of x, because we don't have anything there. It's all zeros. Pretty boring, right? X can be 0, x can be 1, x can be 2, x can be 3, right? And if this is 1, meaning 27 out of 27, let's do it by thirds, I guess, right? So this would be 18 out of 27, and this would be 9 out of 27, right? You buy that? Yes, now? Talk to me, guys. Come on.
Yeah.
So, probability f equals 0 is simply 1 out of 27, right? And the, what color do you want? I'm going to use hot pink for the cumulative, right? Okay. So, f of x is going to be in blue. The cumulative will be in hot pink. Okay. Watch how I do this. Open circle, dot. Open circle means you don't include it, right? Remember on your number line stuff, open circles and closed circles? Remember that?
Mm-hmm.
Then we jump up 7/27 for x equal 1. This is, of course, 7. And 12 out of 27, so we're about right here for x equal 2, right? And then x equal 3, we're back down to 8 out of 27. Okay? So this is what's going to happen with the cumulative. The blue is f of x, the PDF. So the hot pink goes open circle here, and this would be 8 out of 27, right? So the 9 is right there. So I guess this would be a little higher. Okay. So then we stay here because if we could have values of x between 1 and 2, the PDF would be all along this line up to, but not including the point that x equal 2. At x equal 2, we have another increase in probability mass equal to another 12 units out of 27. So this hot pink trace is going to go up to 19 out of 27. Yep, 19 out of 27. Okay. So it's going to be just above 18 out of 27, right? And then it stays there until we hit x equal 3, in which case we jump up to 1. I hope it's obvious to you guys that all cumulative functions eventually go to 1. I hope you see that. Okay? Yes, no? Talk to me, guys. Are we good?
Yep. Also,
Yeah,
10
I'm
minutes.
good.
What? Are you serious? We just started. Oh, man. Thank you. Now, the probability that A is less than or equal to B, less than or equal to X, less than or equal to B, equals, for discrete probability density functions, it's the summation for all values. We're gonna go all the way up to B, right? Where are we gonna start? We're gonna start with A, but it's gonna be, well, here, no. We're gonna start with x equals A, go all the way up to x equal B, and we simply add the values of the probability density function. So, for example, if we wanted to find the probability that x was greater than or equal to 1 and less than or equal to 2, we would simply add these two values. Do you see that? It'd be 18 out of 27, or 2/3. Okay? Yes, no? Talk to me.
Mm-hmm.
Yeah, that makes sense.
Okay? This also equals capital F of B. Because we have the equality, we are including B, minus capital F of A minus. Does everyone understand that? This is totally crucial when it comes to discrete probability functions. We start with the B because we have the equality. This is a great less than or equal to sign. So we want to include the values of B. Okay? So that's where we start. So we would take 9 out of 27, right? And we got to subtract the mass that is below A. Well, do we want below A, or do we want to subtract off including the A value? Well, in our expression up here, we included the probability that X could be A, of X equal A, because we have this equality. So we don't want to subtract out the probability for f of X equal A, or f of A. We don't want to subtract that out. So we go to the left-hand side of A and subtract that value out. Okay, so looking at the probability graph, we start with if A equals 1, B equals 2, for what we have, we start with the cumulative of B, which is up here, 19. Let me write it in hot pink, because that's what the graph is. This is 19 out of 27, yes, no? Right?
Yes.
And we subtract off the cumulative of A. Well, the cumulative of A is the cumulative of 1, but we go immediately to the left of that value. If we went to 1, we would subtract off this value. Do you see that? We don't want to do that because we're including the probability mass due to X equaling A. So we go to A minus. This value here is 1 out of 27. And we get, again, the identical answer to what we had when we only looked at the probability function. So these two expressions are telling us the same thing. Okay? That's the takeaway here. Okay? Now, I hope it's obvious to you now that whether we have the equality or not matters. Okay? And somebody's got an open mic. So I'll write a little table here for you. Okay? For X equaling C, and I'm sorry, for C and D, values of X. The probability that C is less than X, less than D, this equals, you ready? The cumulative of immediately to the left of D. We don't want to add the probability mass due to X being equal D because we don't have the equality here. So we start immediately to the left. Okay? And we subtract off everything. Do we subtract off values from negative infinity to C, or negative infinity to almost to C. We go all the way to C to subtract it out because we're not including the probability mass of X equals C. We're not including that mass. We're subtracting it out. Okay? Now the probability of C less than or equal to X less than D. On the upper end, we have the same thing, right? It's F of X equals D minus. What do we subtract off now, guys?
D minus.
C minus, right?
Yeah.
Very good. Good job, Chris. Was that Chris?
Yeah.
Good job. Okay, let's flip them. What's the probability? What if we had the equality here? Well, this time we're including D, right? So it's F of X minus D minus what?
D.
C not. C.
F of C, right? We're subtracting C and all values lower than C because we didn't include, this range doesn't include the probability mass due to X equals C. Okay, so we subtract off X equals C all the way down. And lastly, which is the function that we have that we started with, C less than or equal to, right? Less than or equal to. We have the equalities for both cases. This equals F of D minus F of C minus, which is what we have over there. Okay? This works for both discrete and continuous functions. Doesn't matter. Okay. In fact, when we go to continuous functions on Thursday, we're going to see that it really doesn't matter if we have the equality or not. The math is exactly the same. Okay. So that's how cumulative density functions work. We'll pick it up here on Thursday. We'll look at continuous functions. Okay. Okay, guys. Any questions?
I'm good. Thank you.
We good? Okay, we'll pick it up here on Thursday, guys. Have a good one. Take care. Be safe.
Yep, you too, Professor.
Have a good
Yep.
one.
You too.